Hi, I'm Zor. Welcome to Unizor Education. We continue talking about certain aspects of physics not usually covered to that particular depth in high school. So that's why I call it Physics Plus. It's presented on unizor.com together with other courses like Math for Teens, Math Plus for all. I also have Relativity and some other courses. Okay, so today we will continue talking about laws of Newton. Primarily we will concentrate on the conservation of energy and how it can be used to solve certain problems which might actually be not as easily solved using the classical method of the second Newton's law. Okay, so here is the problem. Consider you have a horizontal table and there is a chain, half of it is on the table and half of it is hanging down. So we have a mass of the chain, we have a length of the chain, so this is L over 2 and this is L over 2. Let's say this is point A, point AB and point C. Now, let's say in the beginning at time equal to 0, I'm holding the chain so it's at rest. Half of this on the table, half of this hanging down. Now, I let it go, and by the time t equals T, capital T, this half of the chain, since it has certain weight, we have obviously the acceleration of in the gravitation field, it pulls down the chain, considering there is no friction, and eventually it actually slides down all the way, so the edge, which is at point B at the beginning, will be at the very edge of the table. So the whole chain will just be in this position. Half of this is basically right at the top and half is going down. So we obviously assume that there is a floor somewhere, but the floor is below, so the legs of the table are long enough, so the chain doesn't really hit the floor. So I'm talking about two different moments. The beginning, when the chain is at rest, half of this on the table, half of this is hanging down, and at the end of the motion, at capital T time, when the end of the chain is right at the edge of the table. I'm interested in the speed of the chain at that particular end of the experiment moment. Okay, so how can it be actually approached? Well, let's just think about approaching this from the regular standard second Newton's law principle. Force is equal to mass times acceleration. This will be an equation from which we can derive certain law of motion. So what is the law of motion in this case? Well, let's call it S of t. This is how much it slides, this chain slides at the moment t. So S of 0 is equal to 0, and S of t is equal to, it slides half of the length, right? So this is my initial conditions. Now, this is the speed, the first derivative. This is acceleration. And we are interested in V of capital T. Okay, now, this is acceleration, we know that. Now the force is variable, because the more chain slides off the table, the more it weighs actually. The more the gravitation pulls the whole chain. So how can we find it out? Well, very easily actually. In the beginning, the weight which pulls down the chain is the weight of the L over 2, half of the chain. That's in the beginning. Okay, now as the chain slides with this particular law, it's increasing the length of the chain which pulls down. So the length of the chain which pulls down is the initial plus whatever it slides. Now if I have the length and I have the mass of the whole chain and the length of the whole chain, if I will multiply it by m over L, this is the mass density, so to speak. That would be the mass of the piece of the chain which pulls down. And if I will multiply it by g, that would be my force, which depends on the t. And now we can actually have this second Newton's law equation when I have this equals to ms second derivative of t. This is standard differential equation which describes the law of motion, which is s of t. We can solve it using the initial conditions. This is one initial condition. This is another initial condition. In the beginning, the chain is at rest, so the first derivative, which is the speed, is supposed to be equal. So we have initial condition, 2 of them, second degree, second level of differential equation, and we can solve it basically. I mean, first of all, we can get rid of the m. It cancels out, which is very interesting actually. So we see that it doesn't really the motion doesn't depend on the initial total mass of the chain. It's basically like if you will drop two different objects of two different mass from the top of the Tower of Pisa, they will land at the same time. Okay, now, and this obviously we can multiply it by L. Here and here, and divide by L here. And we have a very simple differential equation. S of t minus g L s of t plus g over 2 is equal to 0. Minus. Let me check. Yeah, looks like it. Okay, now it's not that kind of difficult differential equation. We can definitely solve it, but we are not going to do it because there is a simpler method of doing it. So let me just go to a simpler method. And that method would use the law of conservation of energy. So this problem is supposed to demonstrate how powerful these integrated laws of conservation of energy, for example, or there will be some other conservation law, how they are really helping to solve these problems. Okay, so let's approach it differently. As our chain slides down, it's increasing its kinetic energy. So if we know the kinetic energy at the very end of the motion, we will definitely very easily find the speed, because kinetic energy is equal to m v square of t divided by 2. So if we know the kinetic energy, we can very easily find the speed at the end of this motion when the whole chain slides off the table. So how to find kinetic energy? Well, law of conservation of energy. In the beginning and at the end, we can calculate the energy, and that would actually give us the whatever we need. Okay, now the kinetic energy is increasing and obviously there is a source of this kinetic energy. So what's the source of the increase of kinetic energy of the chain? Well, obviously the work which the field, gravitational field, actually performs. So gravitational field performs certain work, and that is the source of increasing the kinetic energy. So let's calculate the work. Okay, how can we do that? Well, again, we know the force, right? The force is equal to, we have already done it, it's 1/2 L plus S of t times m over L times g. So that's the force. Okay, great. Now this force is acting all the time while chain is sliding down. So it's basically applied from S of t equals to 0 to S of t equals to L over 2. So whenever it slides by L over 2, that's the end of the experiment. So why don't we consider S to be an independent variable, and instead of f of t we will have that this is f of s, and instead of s of t we'll just have simple s, where s is a variable, and the s is from 0 to L over 2. So as S is, which is amount of sliding, when S is changing from 0 to L over 2, force is calculated according to this formula. So if I will multiply f of s times ds, differential of sliding, and integrate it from s equal to 0 to L to s equal L over 2, that will give me the work. Okay? Okay, so let's just do it. Instead of f we will put this expression, 1 over L plus s m divided by Lg times ds, and we have to just integrate it, which is a very, very simple integral. Well, it's sum of two integrals. The first one is equal to this times this, which is mg over 2 s. Well, this is a constant, so integral is s, from 0 to L over 2, plus integral of s, which is, so it's mg divided by L. Integral of s is s squared divided by 2, from the same 0 to L over 2, equals. So this is equal to L over 2 instead of s, so it will be mgl divided by 4. And 0 would be 0. Now here would be L squared divided by 4, so it's divided by and 1, this is L, and 1 L will also cancel out, so it will be mgl divided by, so it's 4 and 2 is 8, which is equal to 3/8, right? 1/4 is 2/8 plus 1/8, that's 3/8. So that's my result. So this is the work, and if this is the work, then this is equal to kinetic energy, m v square of t divided by 2. So m cancels out as before, it does not depend on m. So v square of t is equal to, so it's 3/4 of m, oops, no m, gl. So that's the answer. Very simple. So v is equal to square root of this, obviously. So that's the answer, and we did not really do any kind of solving differential equation, which is not really so easy, even in that particular case. One integral, which is very primitive, integral of constant and integral of s, basically. So it's s and s squared over 2. That's simple. All right, so that's basically the answer. Now, let me do it even more energy-oriented way. Instead of using the work, I will use straight law of conservation of energy. So what is the energy of this chain in the very beginning? Well, the energy of the chain is energy of this part and energy of this part. Now, if we are talking about only potential energy, because it's at rest, so kinetic energy is 0. So potential energy, and it's always potential energy is always measuring relative to certain level. For instance, the ground level. In this case, it's more convenient to have it the level of the table to be a level 0 of potential energy. In which case, the energy of the top part, let's say P1, it's equal to 0. Now, the energy of the second part is P2, whatever it is. Now, let's say it slides down. At the very end, it has certain kinetic energy, plus the first part will move down, so it will have some P1 prime, and the second part would move down, P2 prime. Now, what's interesting is that P1 prime, the energy of this part as it actually slides down, would be exactly equal to the energy of this part in the beginning, because they will take exactly the same position. So the first part in the second, at the end of the motion, will take the place of the second part in the beginning of the motion, right? So these two are equal. So from the conservation of law, it follows that this is supposed to be equal to P1 plus P2, right? In the beginning, and this is at the end of the motion. Now, since P1 prime, which is energy of this part at the end of the motion when it takes this position, is equal to P2, I can say that K plus P2 plus P2 prime is equal to P1 is equal to 0 in the beginning, right? So this is the energy of the first part, so it's equal to P2. Okay, this goes down. So from this, K is equal to minus P2 prime. So all we have to do is to calculate the potential energy of the second part of the chain when it moved to this position. So at the end. So when it moves to the end, it takes the position from this is L over 2 and this is L, right? So basically from this point is at L over 2 from the top, and this is at the length L from the 2. Now, how can we calculate the potential energy of the vertical piece of chain? Well, on one hand, it's obviously, intuitively obvious that if we will just concentrate the whole mass in the beginning, in the middle point of this chain, the potential energy of the chain vertically positioned is equal to, and the chain is obviously of the same infinitesimal lengths of the links, etc. So it's very uniform. So obviously the mass, if concentrated in the middle of this chain, would have exactly the same potential energy as the whole chain, because the potential energy is growing linearly. Okay, so in which case the mass of this, its mass of the half of the chain, is equal to m divided by 2. Now the length relative to the table is L2 plus half of the L2, so it's 3/4 of the L. So potential energy would be what? M times G times this, times the length, which is 3/8 of mgl. And again, that's supposed to be equal to mv squared over 2. I mean, we have exactly the same expression for potential energy of this piece as we had for the work, if you remember, before that. So we just equalize it and we will get the v squared. Okay, now what if we are not actually thinking about this intuitively obvious way of calculating potential energy? Let's just calculate it exactly as it's supposed to be using the integral. So again, let's have some small element ds. So we have to integrate its, now mass of this is equal to m times m divided by L times ds. So that's the mass, right? Now we have to multiply it by distance. Well, you know what, it's probably better if I will use, instead of letter S, I will use some other letter X, let's say. So this is X. And X is changing from L2 to L. From L over 2 to L. So this is the mass times G and times distance from the top, which is X. So X is the distance from the top, from the table surface. So this distance is changing from L over 2 to L. So this is an integral. Am I right? Let me check. M over L, G, okay. So now let's take this integral. Integral of x is x squared divided by 2. So it will be m over L G x squared over 2 from L over 2 to L. Alright, so it would be mg divided by L squared over 2 minus L squared over L2 squared is 428. Right? So what is it? Let's check it out. Well, obviously 1L will go out. Now 1/2 minus 1/8 is what? It's 4/8 minus 1/8, so it's 3/8. So I will have again mg L and 3/8. 1L goes from here, so 1L will be in the numerator, and 1/2 minus 1/8 will be 3/8. Again, the same result. So potential energy of this piece is equal to this. Well, actually it was supposed to be with a minus sign because it's below the surface, right? Okay, so that that actually gives the expression for kinetic energy, because whatever increment of potential energy, well, actually increment, it's a decrement, it goes down, so potential energy is decreasing and kinetic energy is increasing. So this decrement is equal to this, the same thing as before. We had many times the same expression, and that allows to calculate the kinetic energy. So that's the kinetic energy and in decrease of the potential energy. So that is supposed to be equal to mv squared divided by 2 of t. Well, from which again we have exactly the same result. V square of t is equal to 3/4 Lg. Okay, so I recommend you to go to unizor.com, go to the course Physics Plus. Actually, it's called Physics Plus for All, and in the laws of Newton, take a look at the problem 2 and just examine whatever is written there. I think when you are reading something after you watch the lecture, it will better inculcate into your mind all these things. And again, as you see, my purpose was to demonstrate that using the laws of conservation is in many cases very, very beneficial relative to the classical approach using differential using calculus, basically differential equations, which are at the heart of the second Newton's law, because this is the second Newton's law. This is a differential equation, whether you like it or not. And in a complicated case, that might be a quite complicated equation. Now, unless you have to know really the whole law of motion, which I was expressing as S of t, which means you have to know for each moment of time position of the chain. I mean, in that case, you just have to solve the differential equation. There is absolutely no other way. But if you don't, if you need only something at the beginning and at the end of the motion, that's exactly where the laws of conservation of energy really are very handy. Okay, that's it for today. Thank you very much, and good luck.